Good day, students. My name is John Obodo. As usual, we are going to be looking at the term gravitational field. Now, the term gravitational field is a concept and a term that we need to understand to deal with the concept of field. However, we need to understand what a field is. Then we look at the major areas or different types of fields, force field and contact force, and their differences. Okay, so this lesson will deal with the concept and calculation of gravitational fields and potentials in the vicinity of various shapes and sizes of massive bodies. And we must have understood and studied what is called electrostatics from our previous classes. Okay, and if you remember from the principle or from the law that we have learned, that is based on the Coulomb's law of electrostatics, we stated that the force of attraction or repulsion between two charges is proportional to the product of the charges, Q1, Q2, and inversely proportional to the square of their distance apart. Okay, so we can have this F equal to K, Q1, Q2 over R squared, where K is a constant, and the K constant is given as 1 over 4 pi epsilon 0, where this is what we call permittivity of free space. E naught is the permittivity of free space. So this is what you have done in the previous class. But in this class, we'll be looking at the term force field, contact force, gravitational field, and their various concepts. Okay? In physics, a force field is a vector field and is a region of space under the influence of a certain force. Talk about certain physical agents such as magnetic, electric, or gravitational. So here, we want to concentrate more on the gravitational field. We need to understand what a force field is and the difference with a vector, what we call the contact force. So a force field, as I said, is a field under the influence of some physical agents that's such as electric, magnetic, or gravitational. Okay, so this is an example of the force field around the Earth. It shows the Earth under the influence of gravity. The gravity here is within the universe and is acting from the stars and the sun especially. So the gravitational pull of the Earth is as a result of the space around it and the force of influence from the sun. So we also have example of what we call the magnetic field around a magnet. This is what we call the magnetic field around the magnet, all right? And the electric field around the point charge. Two charges of dissimilar charges will attract each other. And here we have a north pole and south pole of a bar magnet, showing the lines around this shows the lines of flux or field lines around it. And we also have for the charges. This shows the point charge and the lines of flux around the point charges. And we have what we call field lines. And the field lines can be magnetic, electric, or gravitational. So when we look at this, for example, we consider a case where we look at a condition under the magnetic influence. We have the north and south. We have the field lines around it in this manner. And the field lines are moving from the north to the south, from the north pole to the south pole. So these are the field lines. We call them the field lines. The field lines describe the direction of the field that is in question. And this is the magnet. In this case, that is talking about the magnet. Okay, so that is for that. We can talk about the point charge. For charges, a charge can be a body that is positively or negatively charged and is radiating fluxes. We have a point charge. If it's positively charged, field lines radiate from it in the manner shown. So field lines come out from the point charge. But if it's a negative charge, field lines move into the charge as shown. Okay, so this is an example of field lines acting on a charged body. So when you consider for the Earth, For the Earth, we talk about the polar axis, North Pole and South Pole, and the equator. We have the lines around it. We have what we call the latitude and the longitude. So the Earth at the center, there are fluxes or field lines, gravitational field lines that act towards the center of the Earth. So these field lines are due to the universal gravitational force. And the force that is acting within the universe is as a result of the influence from the sun and other planetary bodies around the Earth. So basically, we talk about Isaac Newton's concept of gravitation. And Isaac Newton's concept of gravitation defines gravitational force as a force that pulls an object towards the center of the Earth. Okay, so that is that concept. Okay, we look at contact force. What is contact force? Contact force is any force that requires contact to occur. Contact forces are ubiquitous and are responsible for most visible interaction between microscopic collections of matter. If you look at the diagram on the slide, we talk about an object with forces acting. We have the applied force, the weight, the normal reaction or normal force, and the frictional force. So that considers an object with a body or an object on a platform with the weight acting vertically downwards, and the weight is mass times gravity, the reactional force, R, or what we call the normal reaction, and we have the frictional force, F, that is pushing the body or acting in opposition to the force that is pushing the object. So this is an object that is being acted by different forces, and these forces are called contact forces, because there must be contact before they exhibit their effect. Okay, so that is for contact force. So a contact force, in most cases, we have examples: reaction, we have tension, we have friction, we have air resistance. These are examples of contact forces. Okay, so we are going to look at the term gravity, which is the main discourse of today's lesson. Now, what is gravity? Now, from the earliest time, gravity meant the tendency of most bodies to fall to earth. In contrast, things that leaped upwards, like flames of fire, were said to have levity. Aristotle was the first writer to attempt a quantitative description of falling motion, and he wrote that objects fell at a constant speed, attained shortly after being released, and heavier things fell faster in proportion to their masses. Of course, this is nonsense. So Galileo was another scientist that tried to explain the concept of gravitational force. And subsequently, we have Isaac Newton's theory, and Kepler, that is Johann Kepler's theory. Now, gravity and gravitational fields are two terms that are used interchangeably. Gravity is a natural phenomenon by which all things with mass or energy, including planets, stars, galaxies, and even light, are brought forward or towards one another. And therefore, gravity gives way to a physical object, and the moon's gravity causes ocean tides. So gravity effect or gravitational field is very important. Now, the term mass is both a property of a physical body and a measure of its resistance to acceleration. So mass is the quantity of matter in a body. Okay? So we talk about the term acceleration due to gravity. Acceleration due to gravity, or what we call the gravitational acceleration, is the free fall acceleration of an object in a vacuum without any drag or force. And this steady gain in speed caused exclusively by the force of gravitational attraction. Therefore, we can say that acceleration due to gravity is influenced or affected by the following factors. One of them is the shape of the Earth. The shape of the Earth influences the acceleration due to gravity. The next one is the altitude, or what we call the height. Okay? And the third one is the latitude of a point within the Earth's surface. Another one is the radius of the Earth. And these four factors are factors that can influence the acceleration due to gravity. Okay, so we have a short explanation that is included there. And with that, you can look at the relationship with acceleration due to gravity in respect to altitude, latitude, radius, and so on and so forth. Okay, the next here has to do with what we call gravitational field and weight. When you talk about weight, the weight of a body is a function of its gravitation. That is, the weight has to do with the gravitational pull acting on a body. Now, we consider the weight of a body with respect to the mass. The weight, which is W, is proportional to the gravitation, G. And therefore, the weight is equal to mg, where m is a constant, m is a mass. That is the mass. And g is the acceleration due to gravity. Acceleration due to gravity. Okay? So if we have the weight equal to mg, our mass will now become weight divided by gravity. And here mass is constant, the weight varies from point to point. And g, which is the acceleration due to gravity, also varies. The acceleration due to gravity varies with the latitude. Because when the Earth's surface, for example, is drawn as shown in the diagram, we have the latitude from a point A within the Earth's surface to another point B. All right, the gravity here may be g. Maybe g here may be 9.81 meter per second squared. But around this point towards the north pole of the Earth, g may vary and become 9.9 meters per second squared. So the value of g varies from point to point. Even on the moon, the value of g is not constant, in the sense that if this is the Earth and g is about 9.8 approximately, in the moon, the value of g is about 1.6 or 1/6 that of the value of the g of the Earth. So that means the gravitational acceleration due to gravity within the atmosphere or within the universe varies with position and with respect to location, and also what we call the latitude. So the value of g is dependent on the shape of the Earth, the altitude or the depth. Also, we talk about the latitude and also the radius of the Earth. Okay, so let's see some examples where we talk about the values of g with respect to weight. If the weight of an object is unknown and the mass, which is constant, is given as 10 kg, and in the Earth, the acceleration due to gravity is 9.9 meter per second squared, we can calculate the weight of the object on Earth. What's the weight? That will be mass times gravity, acceleration due to gravity of the Earth, and that is 10 multiplied by 9.9. And 10 multiplied 9.9 is 99 newtons. That is the weight, 99 newtons. If the weight in the moon is equal to the mass multiplied by acceleration due to gravity of the moon. Okay? The weight in the moon and the weight of a body on Earth are not equal. And if they are not equal, but the mass can be equal, because mass does not vary, but weight of a body varies from point to point. And this is as a result of the acceleration due to gravity of the body. Let us consider a body of mass. A body of mass, 100 kg, that is located within the Earth's surface. G of Earth, let's assume that it is 10 meters per second squared, is taken to the moon. G in the moon is about 1.6 meters per second squared. Let us find the weight. Weight on Earth, question mark, and weight in the moon. Let's see how we can get this two. When we have the mass of the body as 100 kg and acceleration due to gravity on Earth is 10 meters per second squared, acceleration due to gravity in the moon is 1.6 meters per second squared. So the weight in the Earth, or weight in Earth, is equal to mass multiplied by g in the Earth. So therefore, mass is 100 multiplied by g on Earth is 10. So 100 multiplied by 10 is 1,000. So the weight of the body in the moon, on Earth is 1,000 newtons. But the weight of the body in the moon will now be equal to mass of the body times G in the moon. So the G in the moon is 1.6, so we have 100 multiplied by 1.6. And that is 100 multiplied by 1.6 is 160 newtons. And you notice that the weight of the body on Earth is greater than the weight of the body in the moon. And this will tell us that when a body is taken from the Earth to the moon, the body is likely to lose weight, in the sense that a body appears lighter in the moon than in the Earth. And this can also describe the observation that astronauts are found to be floating in the moon, because the acceleration due to gravity in the moon is much lesser than the acceleration due to gravity in the Earth. So therefore, this is also as a result of the shape and size of the Earth. The Earth is much more bigger than the moon. The Earth is much more bigger than the moon, and the moon, on the other hand, is not as big as the Earth. So therefore, we can conclude and say that the weight in the Earth is always larger or more than the weight of a body in the moon. Okay? So in subsequent classes, we are going to look at the effect, or what we call the gravitational field, and concept of what we call the Newton's law of universal gravitation, gravitational potential energy, gravitational intensity, and gravitational field strength. We're going to see what is known as weightlessness, why satellites are located in space, and how they are projected. So with this, we have come to the end of this class. We want to appreciate your watching and listening, and as you continue to do this, we appreciate your effort. Thank you for listening.